So we learned about how you can insert at the front, insert at the end, or insert into the middle using the same common helper method called add between. And symmetrically, we can learn about such useful method for removal purpose as well. That's something I'd like to talk about for this part of the lecture. So the method, well, again, some diagram from the textbook, some reference textbook you don't need to worry about. But anyway, so this is just to illustrate about how to remove a node, so arbitrary node from the list. But I'm going to try to do much better diagram on my iPad. I'm going to do that in a moment. So this is the method I would like to talk about in detail. It's called remove, and we're going to use it as a common helper method for removing from the front, removing from the end, and also removing from the middle. In a very similar way as we reuse the method add between as a helper method for inserting to the front, inserting to the end, and also inserting to the middle, right? In a very similar way. So we really want to achieve maximum code reuse to really minimize code duplicates, right? That's really the reason that why we are introducing the second extension for the header and the trailer. Right, let's now switch to the notes to actually talk about the tracing for this helper method. Okay. And one thing you will notice immediately is about the simplicity of the input parameter. Rather than in the case where you want to add between certain two nodes, you want to pass the elements, you want to pass the predecessor, you pass the successor. But to remove a node, you don't need that because we are not really creating any new nodes. We just want to remove some node. So this would be the only input parameter you have to worry about. So that's the node over here. Okay, and there is one assumption we are making, which is the node actually exists in some doubly linked list. It's actually something you always make sure. Whenever you call the remove method and you want to remove a node, it better be a part of the list rather than the node standing alone by itself, right? And of course, so it is because of this particular assumption. So we will be able to use this remove method here to remove something from the front, from the end, or from the middle. It's really important, as you will see. Okay. Let's now trace this code line by line, shall we? And let's now first of all talk about the first line over here. So we got a predecessor over here. So we got the local variables over here. The local variables, we got predecessor and also we got successor. Predecessor and also we got successor. Let me use a different color for successor. And that's for the successor, right? And the predecessor is defined as the node that get previous, right? This is the node I want to remove. And its predecessor, of course, will be its previous, right? Get previous. And also its successor will be node that get next, right? So what we're having is, so this node over here will be the predecessor of the node that we want to remove. And this node over here will be the successor of the node that we want to remove, right? So that's about these two lines, right? So this line over here and also this line over here. And let's try to set some references. You can see we don't need to create any new node for removal. So in some way, it's actually easier than inserting a node. Let's try to do one by one. So we say predecessor. So predecessor that's set next to be successor. And successor that's set previous to be predecessor, right? Kind of symmetric. Predecessor dot next will be predecessor dot next. Rather than pointing to over here, we want to point to the successor instead. Symmetrically, successor that set previous to be the predecessor. Successor is this particular node. Its previous node, rather than pointing to here, is now going to point to the predecessor. That's what we want to do, right? Let's now do it. So for predecessor next, rather than pointing to over here, it's now going to point to this particular successor over here, right? Let me try to not to really block the text, which will be valuable for you as notes, right? So that's the first one. And also the successor's previous is actually going to be over here, right? And if you really want to see exactly where, think about 1 and also 2. So this is actually 1, and this part over here is actually 2. And of course, I should also delete this particular reference, right? And what about the next two lines? The next two lines, let me use purple. So we say the node dot set next to be null, and node.setPrevious to be null. So this is really to make sure the node that we want to delete will get isolated, so you will get ready for automatic garbage collection. So whenever you really think this node will not be used for any longer, you definitely want to get it ready for garbage collection. In which case, you want to make sure all the pointers pointing to it, or all the pointers it is pointing to, should be set to null. That would be the idea, right? So let's see. So we're gonna say it's so let's call this number 3. This is number 4. Okay. So number 3 would be node.setNext. Node.setNext, rather than pointing to over here, is going to point to just null. Okay. So this would be number 3. What about number 4? Symmetrically, node.setPrevious. So node.previous, rather than pointing to over here, is now going to point to null. So this will be number 4. Right? We got 4 steps. And of course, you also want to decrement the steps eventually. Right? Remember, we are now in the context of the doubly linked list. Right? It's a pretty easy method in some way, because now we are not introducing any new node into the list. Instead, we are assuming that we are removing some existing node from the list. So now let's now talk about how we can use this method as a helper method for removing from the front and from the end first. We'll talk about removing from the middle in just a moment. And before we do that, what's the running time? Well, running time should be quite obvious, right? The running time here, you can simply see each line over here is simply just about setting references, right? And also to get access to the next node just by looking up the next attributes. So it should be just constant. So it's going to be big O of 1. Very efficient algorithm for actually removing a node from the list. Of course, you're given that you're already given the reference to the node. That's why having this particular input parameter is so important. If you don't have this reference over here, in that case, you cannot really have constant amount of time to really remove this node. Just notice that. Okay, let me say over here, efficient solely because the reference of the node to remove is given. Otherwise, if the reference is not given, that would be linear time. It's almost like a remove at a particular position. All right. It's really important for you to actually notice the reference of the node to remove is actually given.